When you pull out your phone and ask for directions, you expect an immediate answer. But the moment your thumb hits the route button, you trigger one of the most complex orchestration events in modern computer science. The system has a hard latency budget of exactly 500 milliseconds to fetch the map, calculate your path, and predict traffic. Therefore, the architecture splits your request into 3 parallel streams: rendering visual geometry, querying the road graph, and running machine learning ETA models. If a single database tried to execute these 3 distinct operations one after another for millions of concurrent users, processing bottlenecks would stretch response times into minutes. It is physically impossible to route planetary traffic through a single pipe. The solution is strict architectural decoupling. By breaking the system into autonomous, independent service layers, each stream operates in total isolation, allowing them to scale horizontally without blocking one another. Reliable planetary navigation depends on the precise orchestration of these distributed systems, turning a massive data challenge into a seamless user experience. The first architectural stream has a roughly 200 millisecond window to deliver the visual geometry of the map to your screen. Historically, this meant asking a back-end database to generate flat image files, raster tiles, for every single pan and zoom. At scale, the compute costs and database query overhead were massive. Modern platforms shift this workload entirely to the client device. Instead of pixels, the server sends Mapbox vector tiles, lightweight packets of pure geometric data containing the coordinates for roads, parks, and buildings. These vector geometries are prepackaged into a single file archive format known as PM tiles. Because these archives are completely static, they can be hosted directly on cheap cloud object storage, bypassing dynamic databases entirely. When you open the map, your browser or mobile app calculates the exact zoom level and coordinate bounding box required to fill your specific screen. That specific request is intercepted by a serverless edge function, like a Cloudflare worker, stationed physically close to your device. To avoid scanning the whole file, the archive organizes the globe using a Hilbert space-filling curve, translating 2-dimensional coordinates into a sequential byte range. The edge worker then issues an HTTP range request, extracting only that exact block of bytes from the bucket. That small vector packet is instantly compressed using Brotli at the edge, sent to your phone and rendered locally by your device's GPU. By combining static object storage with serverless edge compute, the system completely eliminates the dynamic database rendering bottleneck. While the map geometry is drawing, the second stream uses the 200 to 400 millisecond window to calculate your physical path. If you run a mathematically optimal pathfinding algorithm like Dijkstra across a continental road network of billions of intersections, the exponential search space causes the query to stall out and fail. To return a route in under half a second, the industry relies on customizable route planning, or CRP. This technique works by splitting the complex graph math into 2 separate phases. Phase 1 is metric independent. It partitions the physical road network into bounded regional cells, isolating the boundary nodes. The system then pre-computes static shortcuts across these regions, bridging the entry and exit points to bypass the internal residential streets entirely.
Phase 2 is metric dependent. This is where the routing engine injects dynamic weights, like real-time traffic speeds, accidents, or toll costs. Because these dynamic weights are applied strictly to the pre-computed regional shortcuts, the entire continental network can be updated in a matter of seconds. When your route request hits the server, it executes across this customized overlay, resolving a cross-country path in milliseconds. Separating static graph topology from dynamic cost metrics allows systems to perform real-time routing around a fresh accident without recalculating the Earth's geometry. In the final 400 to 500 millisecond window, the third stream must apply highly accurate estimated time of arrival predictions to that route. The raw data used to calculate traffic is incredibly noisy. Billions of GPS pings from user phones are often inaccurate, drifting off-road or dropping out entirely. To clean this up, the system processes the telemetry through a hidden Markov model, using the Viterbi algorithm to probabilistically snap those erratic pings onto exact physical street segments. But knowing current traffic speeds isn't enough. If your drive takes 40 minutes, an accurate ETA requires predicting bottlenecks that won't even form until you're halfway there. The model must account for the chaotic reality of urban traffic, like the dense congestion in São Paulo, where localized braking cascades into miles of gridlock. It also must generalize across entirely different urban layouts, such as the multi-directional, stop-and-go flows of heavy intersections in Tokyo. To solve this, researchers partition the road network into supersegments, grouping multiple adjacent streets that share significant traffic volume into a single manageable block. They then process these supersegments using a specific machine learning architecture called graph neural networks, which utilize a message passing mechanism. Nodes representing road segments share their current state and traffic conditions back and forth with their immediate neighbors. This constant exchange allows the model to learn relational routing biases. It learns the connectivity structure of the roads, enabling it to predict how congestion on a side street will eventually spill over and affect traffic on the main highway. Deploying this spatiotemporal reasoning cut ETA prediction errors by up to 50% globally. Graph neural networks successfully untangle the combinatorial nightmare of traffic prediction because they process the physical connectivity of the world rather than evaluating isolated data points. Exactly as the 500 millisecond latency budget expires, all three of these parallel streams converge back on your device. First, your local GPU renders the PMTL's vector data, drawing the physical world. Second, the interface overlays the precise path calculated by the customizable route planning engine. Finally, it stamps that route with the dynamic ETA generated by the graph neural network. Handling planetary scale demands strict architectural decoupling. If the massive machine learning model is retraining, or there is a sudden spike in noisy GPS telemetry ingestion, those back-end stresses will never block the serverless edge from delivering your visual map tiles. The ability to navigate the planet in real time emerges from the convergence of these isolated, highly specialized infrastructure layers, all meeting on your screen in the blink of an eye.